Hi everyone, welcome to the notes over geometric sequences and series. So a geometric sequence is one in which the same number is multiplied or divided by to get each term next in the sequence. The number you multiply or divide by is known as the common ratio. And we're usually using the letter R to represent the common ratio. So what we're going to do in example number 1 is to determine if the following sequence is arithmetic, geometric, or neither. So looking at our first sequence, okay, we notice that from 1 to 2, we add 1, but from 2 to 6, we add 4. So we're not adding the same number each time, so therefore this tells us that it is not arithmetic. So then we think about multiplication. From 1 to 2, I multiply by 2. But from 2 to 6, I multiply by 3. So therefore, this is not geometric. So if it's not arithmetic and it's not geometric, then it is going to be neither. Okay. Looking at B, okay, I noticed from 81 to 27, it looks like it's dividing by 3. Okay, and then from 27 to 9, it's dividing by 3. From 9 to 3, it's dividing by 3, and from 3 to 1, it's dividing by 3. However, when we do geometric sequences, yes, we can say that it's dividing, but our common ratio cannot be dividing. A common ratio is what we're multiplying by each time. So what we need to know is that dividing by 3 is the same thing as multiplying by 1/3. So that's super important for us to know on this right here. Dividing by 3 is the same thing as multiplying by 1/3. So if we look at it, we're dividing by 3. That means that it is geometric. And my common ratio is going to be 1/3. Because again, we need to change it from dividing by 3 to multiplying by 1/3. Okay, looking at the next one, I see from 5 to 10. I could say it's multiplying by 2, but 2 times 10 is 20, not 15. So then I think about adding, and I see that it's adding 5 each time. Okay, each time we add 5 to get to the next number. So therefore, this is an example of arithmetic. And my common difference is 5. Okay, then we have two formulas. Our first one is the explicit formula. This explicit formula tells us just a general rule or a general equation for a sequence, and then it can be used to find the nth term of a geometric sequence. Okay, so a sub 1 is the first term and R is the common ratio, and this is the formula that we have right here. Then we have our recursive form, and our recursive form tells us that we just need our first term and our common ratio, and then we just plug our information into this. Now, one thing I do want you to know is that this part right here can be rewritten or written in a different order. So just so you know that R times A sub n minus 1 is the same thing. Okay, multiplication is commutative, so it does not matter which one is written first, and then that first part stays the same. So looking at example number 2, It says the third term of a geometric sequence is 64, while the common ratio is 2. Write the explicit rule for the nth term, find the ninth term, and then write the recursive form. So we're going to focus on part A. Part A wants us to write an explicit rule. Well, the explicit rule means we're going to use this equation up here. So I'm going to go ahead and just rewrite that equation so we can talk about it. So for this rule, we need the common ratio and the first term. We were given the common ratio in the directions. It says the common ratio is 2. So we know R equals 2. Then we need to know the first term. But instead, we were given the third term of the sequence. The third term is 64. So what we have to do is we have to think, here's my first term, then I have a second term, then I have 64, and then I would have the next term, and then it would keep going. Well, to get the fourth term, we were told we would multiply it by 2 because that's our common ratio. So if I want to go in the opposite direction, I'm going to do the opposite of multiplying by 2, and I am going to divide by 2. So dividing by 2, 64 divided by 2 gives me 32. 32 divided by 2 to get that first term is 16. So now I know my first term is 16. So all we have to do now is plug this information in for a sub 1 and r, and then we have our explicit rule. So we have a sub n equals 16 times 2 to the n minus 1 power. And that would be our explicit rule. Looking at the next one, we want to find the ninth term. Well, we're going to use the same formula that we just came up with, but instead of the n's in both of those formulas, we're going to replace it with 9 because we want to find the ninth term. So when it asks you to find a specific term, that tells you what your n value is. So again, I have a sub 9, and it's going to equal 16 times 2 to the 9 minus 1 power. And now all you do is type this piece right here into your calculator. So when we go to our calculator, we're going to do a new document, a new calculator, and we're going to type in 16 times 2 to the 9 minus 1 power. We get 4,096. So a sub 9 is equal to 4,096. Now we want the recursive formula. So for the recursive formula, if we look back up at the top, we needed two things, the first term and the common ratio, and then we just plug it into this form. Well, we found both of those in part A. The common ratio is 2. The first term is 1. Or sorry, the first term is 16. So I have a sub 1 equals 16. Then I have a sub n equals my common ratio of 2 times the previous term, a sub n minus 1. And that's it for the recursive formula. Okay, so make sure you feel comfortable with those formulas, and if you have any questions, write them down there. Now looking at the back, we're talking about the sum of an infinite and a finite series. So finite means that it is a countable number of things. They will give you a specific number of terms to find the sum of. When that is the case, this is the formula you will use. Okay, this formula is probably used more than the other one, but if it says find the infinite sum, then we use this formula over here, and our r, the absolute value of our r, has to be less than 1. Okay, so let's go ahead and apply these to some examples. Find the sum of the first 10 terms of the series. So since it gave us a specific number of terms, 10 terms, That means we're going to use this first formula right there. Okay, so I'm going to go ahead and just rewrite out the formula. Okay, so let's identify our key pieces. The first term, well, we look at our series, that would be 1. Okay, then we need to identify our common ratio because that goes in 2 different spots. So from 1 to 5, I am multiplying by 5. From 5 to 25, I'm multiplying by 5. And from 25 to 125, I'm multiplying by 5, which tells me my common ratio is 5. Then we need to identify n, which how many terms are we trying to find the sum of? And that answer is 10. So n equals 10. All we're going to do is plug that into the formula and then use our calculator to evaluate. So I have S sub 10, which just means the sum of the first 10 terms, equals my first term 1 times 1 plus the common ratio 5. Oh, I'm sorry, it should be a minus sign. I am using the wrong formula, so let me fix that. Those should be minus signs. There we go. To the 10th power, all divided by 1 minus 5. There we go. So make sure you fix that because I did have the incorrect sign. So now we're going to go ahead and type this part right here directly into our calculator to evaluate. So I go to my calculator. I'm going to start with the fraction button. I have 1 times 1 minus 5 to the 10th power. On bottom, I have 1 minus 4. I'm sorry, 1 minus 5. I type it in. I get this answer right here. So 2,441,406. So S sub 10 is equal to 2,441,406. So when you find sums of geometric series, they could be really big numbers, or sometimes they could be fractions. That's perfectly okay. Now, example 4 is using the same sequence from example or series from example 3. So find n such that S sub n is equal to 3,906. So one thing you need to pay attention to is that this sum right here is smaller than the sum that we just got, which means n should be less than 10. Okay, so that's just something to keep in mind. So we have S sub n equals 3,906. So I'm going to plug in what S sub n equals. That's that a sub 1 times 1 minus r to the nth power, all divided by 1 minus r. And again, that equals 3,906. So now what we're going to do is we're going to plug in what we can. We know the common ratio, and we know the first term. We're trying to solve for n. So I'm going to plug in that information. So I have 1 times 1 minus 5 to the n power. We don't know n. All divided by 1 minus 5. So, and that still equals 3,906. Oh, let me use the correct color to color coordinate. Okay, now what I'm going to do is I am going to simplify this piece right here. 1 minus 5 is negative 4. So I'm going to write that right here because I ran out of space. So, and then also if we think about it, 1 times anything is just going to be that anything. So I'm going to go ahead and distribute that 1, and I still end up with 1 minus 5 to the nth power divided by negative 4 equals 3,906. Now, I want that 4 out of the denominator, so I'm going to multiply both sides by negative 4. That cancels that out. It leaves me with 1 minus 5 to the n power equals 15,624. You could type that into your handy-dandy calculator. So then what I'm going to do is I'm going to add the 5n to both sides. and I'm going to subtract the 15,624 from both sides. I'm sorry, that should have been negative, so I'm going to add it to both sides. So when I do that, I get 15,625 equals 5n. Okay, so I want to solve for an exponent. So this is exactly like our previous unit was. We have two options. You can rewrite them with the same base, or you can convert to log form to solve. So as a reminder, if I have a base raised to a power equals a number, to convert to log form, it's log base b of the number n equals the power. Okay, so that is the conversion that we did in our last unit, and that's the method I'm going to use. So I have log base 5 of 15,625 equals n. So now all we're going to do is we're going to type this piece right here into the calculator so we can identify what number n represents. So I go to my calculator, I hit my log button, control 10 to the x power. I have my base of 5, I have 15,625, I press enter and I get 6. So I get n equals 6. So the sum of the first 6 terms is that 3,906. Now, looking at the last example, number 5, we want to find the infinite sum of the series. So what we need to do is we need to first understand that we are using this second formula right here. Okay, we need to make sure that our r is less than 1. The absolute value of our r is less than 1. But we're also going to write down that formula. Okay, so that would be s equals a sub 1 divided by 1 minus r. So we need to identify our a sub 1. We need to identify our r. And again, we need to make sure that our r's absolute value is less than 1. So if I look at it, my first term, okay, is 512. To go from 512 to 64, we're dividing by 8, but remember I said in example 1b that is multiplying by 1/8. Then 64 to 8, again multiplying by 1/8. 8 to 1, that is multiplying by 1/8. So my r is 1/8. Well, the absolute value of 1/8 equals 1/8, which is less than 1. So we can use this formula right here. All we have to do is plug in our first term, plug in our common ratio, and evaluate. So we get s equals 512 divided by 1 minus 1/8. Again, we're just going to type this into our calculator to evaluate. So I go to my calculator, I start with my fraction button, I have 512. On bottom, I have 1 minus 1/8. Press enter, I get 4,096 divided by 7. So s, the infinite sum, s is equal to 4,096 divided by 7. And that would be it. So if you have any questions over finding the sum or anything that we've done in this video, please write it down and make sure you ask in class. Have a great day.